Okay, so earlier this morning we saw how to write static scenic scenarios, you could say. They're just describing scenes, so configurations of objects at one point in time. How can we add dynamics to that to say how things move and behave in other ways? So Scenic can describe what we call dynamic agents, which take actions over time, and they can react to the changing environment. It doesn't have to be like a pre-programmed fixed sequence of actions. You can define a policy saying, as a function of what's going on around, this is how the agent should behave. So, for example, we could extend that badly parked car scenario we gave before to say, now, not only is it a badly parked car, but as the ego car drives towards it, it suddenly pulls into the road. This is the kind of thing we'd like to encode. The way in Scenic that we do this is by giving the car what we call a behavior. So here's that bit of code we had before from the parked car example. I've added a third specifier here saying with behavior pull into road. So behavior is a property that's built into Scenic, which basically says the policy that this agent should follow. And these policies are called behaviors in Scenic, and we have syntax for defining those policies. So before we get into the syntax, let me just describe what these behaviors are. The way you should think about them is they are like functions which run in parallel with the simulation. So the time is flowing in the simulation, the behavior is running at the same time. In Scenic, we have a discrete notion of time. So you fix a time step, and time advances in these steps. The simulator might have a different notion of time. It may be, doing a much finer time step to simulate physics more accurately, for instance. You could use a much longer time step in Scenic. But you do specify some time step, and then there are these discrete times. At each time, agents take what we call actions. You can think of these as like the primitive kinds of behaviors that a simulator would support. So the picture you should have is that in Scenic, we've got the behavior for some agent. Maybe you've got a bunch of these running. They're all running in parallel for all of the different agents that you define. At every time step, they send these actions like apply the brake or turn the headlights on, something like that, over to the simulator. And then, so for the autonomous vehicles, could be set the throttle, set the steering angle, turn on turn signal, these kind of things. Scenic itself doesn't define these because they tend to be domain specific, these actions. So for example, the driving domain library that we saw before, when we imported it, the first line of that parked car scenario defines throttle, steering, various actions like that, which are then implemented differently by the different simulator interfaces. Okay, and the idea of this is that then you don't need to know, like, how do you set the brake in Carla? You can just use the Scenic driving library way to set your brake, and that will work in Carla and SVL and other driving simulations. Okay, so you've got the simulators over there, and then what comes back every time step is the updated state of the world. So the simulator is simulating physics, things are moving around, the cars are driving, the simulator sends back to Scenic at every time step what's the new position of everything, the new velocity, and so forth. And so Scenic then updates the objects in the scenario with the new positions and so forth. And these behaviors can access those to make choices. So our car could decide, for example, how to follow a lane based on its current position. So in fact, our driving library has a built-in behavior or a behavior that it defines called follow lane behavior. If you look at it, it's actually pretty complicated because it handles things like what do you do if you get into an intersection. But in essence, what the structure of the follow lane behavior is it's an infinite loop where at every time step you pick some throttle and steering based on your current position. So like if you're to the left of the center line of the lane, you should steer to the right. You compute the throttle and steering that you want somehow, and then you use this Scenic state, the take statement, to take actions. So here we're taking two actions. We're a set throttle action and a set steer action. These are both defined by this driving domain library, and they do what you expect. We're saying set the throttle to this level of throttle, set the steering angle to this number. And the semantics of these of this take statement is it tells Scenic, okay, in the current time step, in the current time step, here are the actions this behavior would like to take. this agent, the agent that's running this behavior. Scenic will then pause the execution of this behavior, wait for all the behaviors to pick what actions they want to take. So all the cars, if it's a driving scenario, they all pick what they want to do. We ship those over to the simulator. Simulator simulates physics for one time step. We read the positions back, and then we resume executing all the behaviors. So in this case, the take statement will finish, this loop will iterate again, and we'll compute a new throttle and steer. Question?
Can behaviors be dependent on each other?
So the question was, can behaviors be dependent on each other? So behaviors are like functions. They can have their own local variables, which another behavior could not read. But behaviors could communicate through global state. So if you want to, for example, you could have a behavior that sets some global flag at some point, and another behavior reads that. We don't provide more like high-level constructs for communication between behaviors, like channels or queues or something like that, because it hasn't really come up. If you have a use case where you would need that, let us know, because we consider adding something. Most of the examples we've written, the behaviors, they will react to other agents through global state. Like you would drive depending on where you see the other car is, right? But you don't need like radio communication with that car. You just see like where is that car, and you make a decision based on that. But if you do need like actual communication, like data going back and forth between behaviors, that is possible through global variables.
I mean, I think it's also, you could extend the library, the domain library with objects that may correspond to communication.
Yeah, you could. Right. Yeah, all I mean is
then you can
those aren't-
define actions that will read or write from those channels.
Yeah, you could. Oh, Eric,
If you do modify global state, there are some caveats of like the order in which the behaviors are.
that's true. Right. So yeah, it gets, if the behaviors are reading and writing each other's state, then it becomes a question of like which one gets to write and read first, right? And that the order and things like that is not important if you're just doing these actions, because they all get sent to the simulator at the same time, basically. So there are some pitfalls there, but yeah, it is possible. If you need behaviors to communicate with each other, they can.
So
Yes.
here the simulator is restricted to the ticks followed by Scenic.
It's not actually. So in fact, in Webots, for example, when we run up examples there, we might use a Scenic time step of 1/10 of a second, but Webots is using 1/30th of a second physics, right? So they don't have to line up. You could have the simulator could have multiple ticks for every tick of Scenic, and that might make sense because Scenic is generally controlling like more higher level behavior. But it's customizable. You can set the time step. Obviously, the smaller the time step is, the more overhead you have of going back and forth between Scenic and this. Okay. So this is just an intro to the very basics of how behaviors work. Now you can write a lot more interesting things than that. There's just this one, which is just constantly taking these throttle and steering actions with different parameters. So for example, Scenic has a concept of interrupts, which allow you to add a special case to some existing behavior without modifying its code. So for instance, maybe you want to say, let's do the follow lane behavior, which is built into the library, but I don't want to do that until some condition is met. Maybe once we get close enough to some other car, then I want to switch to some other behavior, some collision avoidance behavior. Scenic has this try interrupt statement to help with that. So the semantics of this is we start running the code inside the try block. So here we're using the do statement to invoke a sub behavior. So it's like a function call, but it's a call to another behavior. So it basically says, I'm not going to issue any actions right now. I'm going to call this other behavior. It's going to issue actions. Until that behavior finishes, then give control back to me. That's what this do statement does. So this is saying do follow lane behavior, but while the follow lane behavior is running, monitor this condition, the distance to the other. It's from the ego because I didn't specify the other object, so it's the distance between the ego and other. And if that gets less than the safety distance parameter, then we're going to interrupt the follow lane behavior. So we're going to pause it, give control to this other behavior, collision avoidance. When collision avoidance, that behavior finishes, we'll check, is this condition still true? If so, we're going to run collision avoidance again. But if this condition is false, then control will get pass back to this. So resume wherever we left off inside the try block. So you can think of it, it's sort of like, if you think, actually I forgot to mention before, the syntax of Scenic looks a lot like Python. By design, Scenic interoperates with Python, and you can basically use arbitrary Python code inside Scenic. You can call out to Python functions, etc. So this looks a lot like the try except block in Python, where you do something, but then if an exception gets raised, you go to this exception handler. It's sort of like that. The key difference is control can go back inside the try block here. So the interrupts are, in a sense, like temporary. That once the interrupt handler has finished, unless another interrupt is going to fire, control gets passed back into the try block at whatever point it was suspended. So maybe you spent like 5 steps in here, and then you have the interrupt handler, then we'll resume this at wherever point we left off. So if follow lane behavior was a behavior at like 100 lines, if we were on line 30 when we suspended it, that's where we will resume executing it again. Yeah.
Yeah, so I'm asking this distance thing, when do you check it? Every step or like
Every time step.
every time step?
Every time step. Right.
So there is a time step thing.
Yeah, it's the Scenic time step. So whatever time step that was set to be, that's how often we're checking.
So if you are doing that in simulators, which time step thing?
Yeah, so here this is happening just purely on the Scenic side.
Okay.
So nothing here like is calling out to a simulator explicitly. Right. So this gets to the issue of like how do you pick the time step? If you pick a smaller time step, then you'd be able to check this condition more frequently, right? But you have more overhead of going back and forth between Scenic.
We'll be covering this synchronization of time step between Scenic and simulator in the afternoon.
Yeah, exactly. When we talk, so this afternoon, we're going to talk, thanks Sanjay for reminding me, we're going to talk about how do you interface Scenic to a simulator? And we'll see exactly what the communication back and forth is. Yes.
So are there a dictionary of the academic construct, for example, follow lane behavior and all, and then for a custom one, I have to field a proposal?
Right.
Or can I define my own custom academic behavior?
Both, you can do both. So follow lane behavior is not atomic really as far as like Scenic is concerned. It's actually defined using the same syntax, this behavior thing. In fact, maybe after I'm done with the slides, I can go show you the source for this. You can read it. It's defined in the same way as the only part that is actually like the really low level part that has to be atomic. These are the actions, like set throttle action, set steering action, these kind of things. If we look at the implementation of those, you'll see those vary by simulator. So for example, this code, if we ran this in Carla, the follow lane behavior is not customized for Carla. The same code will run in Carla and in say SVL. But the set steering action will do something different in Carla and SVL because it has to call a Carla specific API to set the throttle of this car. And the other simulator has to set it different. So the actions are the part that the simulator interface has to define, saying here are the actions that this simulator supports. Everything else, like the higher level behaviors, like following lanes and things, these can be written purely in Scenic.
So with those behaviors will then be constructed based on those atomic
actions. Exactly, right. Along the lines of this. So here follow lane behavior is calling these atomic actions here, set throttle actions and steer action. So these are these aren't simulator specific, but the implementation of these is simulator specific. So we'll see that later sections too. Yeah.
So is this behavior static or you can modify it out because the simulations like because the car following is depends on the speed itself.
Right. Yeah. So a good question. So like if we have this follow lane behavior,
Repeat the question.
oh, so the question is like, is this behavior kind of static or can you have it change over the course of the simulation? That's one of the key reasons why we have these interrupts is to allow you to customize these without having to change their code. So like I said, follow lane behavior is actually like 100 lines of Scenic or something because it has all this stuff. Right? What do you do in intersections, that kind of thing? It would be really annoying if to do something like follow lanes, but now, at a particular time, maybe 5 to 10 seconds in, switch to doing something else. We don't want to have to put an if state inside the follow lane behavior. So the interrupts are what let you do this. So here you can basically say, do the follow lane behavior until some condition is met, then switch to do something totally different. Right? So we can say things like, all right, do this behavior under this condition, under this other condition, use this other behavior, etc. And the built-in ones like follow lead car or the follow lane behavior provide some parameters like the speed you're trying to follow, etc. So you can customize them. We don't have a big library of these built in to see in the driving domain. We just have a few like follow lane behavior. This is something we're working on, like building a bigger library of these things. And we also are planning, maybe we've already started working on actually hooking in some human models. So you could say like drive in a human-like way. The ones we have built in are relatively simplistic, basically, just so that you have basic kinds of behaviors like following lanes, following given trajectories, etc.
Is it important to create objects dynamically?
Good question. So the question was, oops. Can you create objects dynamically? You can create objects dynamically in Scenic. This is somewhat more of an advanced feature, so I think I'll probably touch on it towards the end of the hour here. But yes, it is possible. Not every simulator interface supports that. Some simulators require you to kind of set up ahead of time what all the objects involved in the simulation are, and then those wouldn't support this. But Carla, for example, yes, you can create cars dynamically. So you can do things like have the car be driving along, and as you approach an intersection, create somebody around the corner who can drive.
And create something dynamically in the cone, like the cone of that.
Yeah, exactly. You could say things like create a car that's visible, or you could actually, you might want to say create a car that's not visible so that it doesn't just suddenly appear, because that wouldn't be very realistic. But you could have it say like it should be on the road around the corner but not be visible. And you could have it create that. Yeah.
Do you have any tie-ins with Sumo that integrate similarly?
Yeah, good question. So we don't have an interface to Sumo,
Well,
but
we have this experimental interface. Yeah, there was a group at in Florida at Embry-Riddle Aeronautical University that created an experimental Scenic Sumo interface. And so it's nothing that we've tested, but it's something that you could build on if you're interested. Okay, happy to talk to you.
Thanks. I had forgotten you're using Sumo. So.
Yeah, I think we should have a page on our website that links to projects by others.
Right,
Yeah,
but we should.
don't have that
And
yet,
Sumo is popular enough that I think it would be nice to merge that into Scenic itself. Okay. All right, so that's interrupts. And we'll see some more examples of that when I get over to the notebook. I also want to mention, just like we had in static Scenic, we had this require statement. Actually, I may not have gotten to the examples, but you can say like require X can see Y. And then that's a requirement that Scenic will enforce. So it's basically taking the distribution that you defined in the Scenic program and then conditioning that distribution on that requirement being true. You can do the same thing with dynamic simulations or dynamic scenarios. So these are examples of temporal requirements written in temporal logic. So we support the operators from linear temporal logic. For those of you who know what that is, basically what this is saying, require always that the taxi be in the lane. So here I'm using this in operator, which is checking, is this object in this region? So maybe I've picked a particular lane. And this is saying at every time step, the taxi should be in that region. If it's not, at some time step, Scenic will throw out this simulation and try to find a new one. Here's a different one where we can say, I don't need this to be true every time step, but I need it to be true at some point during the simulation. At some point, the ego should be able to see the pedestrian. This is using the can see predicate. So this is like the ray tracing type check that I mentioned before.
Yes, second is dependent on the behavior of the.
It is. So Scenic is going to be checking this during the simulation. If the simulation finishes and at no point was the ego able to see the pedestrian, Scenic will say, this did not satisfy our requirements, throwing out the simulation, let's generate a new one. So it's possible to write requirements that cannot be satisfied, right? Or would be very difficult to satisfy, in which case, in the worst case, Scenic falls back on rejection step. So basically, we're just going to be generating lots of things. And if Scenic is not ever able to find something, it might just run forever, or at least hit some limit of like, I tried this many times and I couldn't come up with anything. So that's the The pros and cons of this is Scenic allows you to put arbitrary constraints on. They can be arbitrarily complicated. The downside is that Scenic is not omniscient. It can't necessarily figure out how to satisfy these. As I mentioned before, when we talk about the internals a little bit tomorrow, I'll mention it. We do have some reasoning in Scenic to try to improve the probability of requirements being satisfied. But ultimately, you may have to do a little bit of engineering here. If like you write a requirement that has very low probability of being satisfied, it may take Scenic a long time to find that. And you may need to adjust how you wrote the scenario to make these have higher probability. Okay. So that gives you an overview of the key kind of constructs for dynamic scenarios in Scenic. So let me go through an example now in more detail. So the Badley Park car one that Sanjit showed actually is in the examples in our repository. If you want to see that one, I'm going to do a slightly more complicated one to illustrate a couple of extra things that the Badley Park car one doesn't show. So this is from the OAS Voyage set of scenarios, if you know about those. What's basically happening in this one is there's a lead car, which is periodically stopping and starting. Ego car behind it has to follow it, but brake to avoid a collision. So let's see how we could model this in C. So we're going to use this follow lead car behavior that I already showed. Here's the behavior we'll use for the lead car, stopping and starting. So what we're going to do is we're going to pick a random time to have a delay between the different stops and starts in this car. Okay, and this behavior is going to have some state, some internal state. It's got a local variable last stop here, which we're going to use to keep track of the last time we did one of these stops, so that we can do this stopping and restarting. And then what we're going to do is we're going to follow the current lane at some fixed speed until the current time in the simulation. So here we're using this built-in function simulation, which Scenic has to basically expose some basic information about the currently running simulation. This is also a way you can get access to simulator-specific APIs if you have to do something that Scenic doesn't know about. Like, say, in Carla, you want to like turn one of the traffic lights on or off. You need to use some simulator-specific thing for that. You can access that through this thing. Here we're just saying what's the current time, and we're seeing comparing that to the last time we stopped. So this is going to be the time elapsed since the last time we stopped. If that's greater than this delay we chose earlier, then this interrupt will happen. We're going to do this full braking behavior, which I haven't actually shown, but it's just a loop which says apply braking of 1 and throttle of 0. We're going to do that for 5 seconds. So Scenic has a couple of clauses that you can tack on to the do statement here to control how you're using this sub-behavior. In this case, we're saying do it for a maximum of 5 seconds. You can also add conditions and things on here. We'll see some examples later. So we're going to do braking for 5 seconds. Then we'll update our state here of when the last time we stopped was. And now this condition will be false. So the interrupt, when we reach the end of this here, the condition won't be true. So we will resume follow lane behavior until this condition becomes true again. So the end result is that we're going to have these 5-second pauses where the gap between each of the pauses is this random time between 3 and 6 seconds. Questions about any of this syntax? So the key thing I want to point out here is that you notice that the behaviors can have their own internal state, so they can have memory here. Like here's remembering how much time has elapsed. They can look at global state as well. Like here, we're looking at the distance to some other car, the current time in the simulation, etc. And there we have ways like the interrupt statement and the do statement to orchestrate, to basically combine simpler behaviors into more complicated. Okay, so we've got the behaviors now. So let's set up the cars. So we can do something pretty straightforward here. We'll say the ego is just a car somewhere on the road. We won't specify where. It's going to use this follow lead car behavior. The lead car will place it 10 meters ahead of the ego with stops and starts behavior. Notice here, I'm not actually saying that this other car has to be on the road. It could be, imagine you're on a curved road, and if you went 10 meters ahead, you're now like off the road, right? But because in the car class, we have this default requirement that cars have to be on the road, we're only going to get scenes where both cars are on the road. So basically, the road is going to have to be pretty straight in the starting part where we're creating this, at least within this 10-meter region. Okay? But then actually, for this one, I've forgotten before, I actually do want this one to be on a straight part of the road. So I'm adding a requirement here where I'm saying, if we take a point ahead of ego by 100 meters, that should also be in the road. So that's kind of forcing that 100 meters ahead is still on the road. Now, this is just a very simple thing I put in. You could imagine maybe it's the road curves and then went back. You could also, I didn't want to get into it here, but Scenic's driving library lets you query information about the road network. So you could do things like iterate over all the roads, only select the ones which are straight, and create a car on a random one of those. But I didn't want to show that here. We have some examples which do things like that. Like they say, randomly select a lane from all 4-lane roads. Take the slowest lane, the slow lane, right? The one next to the bike lane, something like that. Okay. Oh,
So,
yes.
so the hard constraint is that the car cannot be rendered on the top of the curve or something. Are they also implemented dynamically?
That one is only for the initial condition. Yeah, the default requirement that cars be on roads. I mean, you can look at how it's defined in the driving model. We can look at that later, but it's just for the initial condition. So it doesn't prevent a car from like driving up onto a sidewalk. Because you might want to find a case where you, like your AV does drive up onto a sidewalk or something. If you wanted to rule that out, you could add a line saying like, require always ego in road or something like that. And then if the ego ever left the road, Scenic would reject that simulation and try to find it. Okay, so the last thing I'm adding here is a termination condition. When do we want the simulation to end? By default, it'll just run forever unless you specify, like on the command line, when you're running Scenic, like how long do you want to run this for? But you can also add in various conditions under which to end the simulation. So here I'm actually saying to end this when the ego car is no longer in a lane. Don't remember why I put that one in. I think we probably also have a time limit, but I've just put this in so that if the ego does actually go off the road, we stop it at that point. So this like underscore lane thing is something in the driving domain, which either is the current lane that the ego is in or none if it's not in any lane. Okay. So
this ego, what happens when the ego is trying to switch the lane?
I believe it's the lane under the center of the ego. So this will change instantaneously from one lane to another as it crosses the center, the like dividing line. All these kind of driving domain specific APIs, I'm not going too much into them here because they're specific to driving scenarios, but these are all documented in the Scenic documentation. Also, there's a page on driving domain and the APIs we have for getting information about the road network and stuff. Okay, so if we actually want to run this, I can run this on my computer. Maybe I'll show you that in just a second, but I can't run Carla on my computer because it needs a big GPU. Maybe some of you have laptops that can run Carla, but most laptops won't run on. So I'm just going to have videos showing this, but we do have a simple simulator built into Scenic, which we call the Newtonian simulator. This is the one that is used in the Google Colabs, so I'll show that in a bit. And it's really intended for debugging. It has extremely simplistic physics, like it doesn't detect collisions, so cars will just like pass through each other. But it allows you to at least visualize what's going on in a scenario. But really, most of these dynamic ones, you should connect to a simulator in order to run. We were hoping to have it ready for this workshop, but it turned out to be more complicated than we were hoping. We are interfacing Scenic to another simulator called MetaDrive, which is relatively easy to install and has better physics than our Newtonian one. So for driving scenarios, hopefully that'll be in soon. And that will be a much lighter weight simulator than Carla and these other ones. So you can play around with it on the personal machine. But for the moment, this Newtonian simulator is the easiest thing. Okay, but here's what it would look like if we take that scenario and run it in Carla. So you can see the two cars. The one in the front is going to stop. That triggered the emergency braking. This one, we got the 5-second delay, and then it's going to start again. Okay. I'll let this run for a little bit longer, and then I think we will get a different sample of this. Here we go. So here's another sample of the same scenarios. Now we're in a different part of the map, but the same kind of overall behavior. Let's see one more sample, because I think the next one is more. They will be on a curve, but right? Maybe not. Oh, that's the end of the video. Never mind. Different video. Okay. So I was hoping to do, well, we'll see this afternoon when we do give you a chance to write your own scenarios. If some of you want to play around with dynamic ones, you can do them on your own computer in the Newtonian simulator or in the Colab notebook. I'll show that in a second. If it's working, I'm going to try to remote desktop into a machine where we have Carla. So if you want to send me some of the scenarios that you've written, we can try showing them in Carla. However, apparently there was a kind of malware attack on the data center and they locked it down. So I emailed them to see if we can get in, but we'll see. So that may not happen. Okay, let's go over to the notebook. Okay, so this is the second Colab notebook is linked to from the schedule. I've already run the setup thing here. There's just description basically reminding you of what I was talking about, of what actions and behaviors are. And let me show you how this runs. So in this particular notebook, what we've done is we've set up this Jupyter Magic thing here, this Scenic Simulate, which takes the Scenic code that you write, samples the scene from it, and then runs a simulation from it, from that scene in the Newtonian simulator, renders it as a GIF, and then inserts the GIF in here. So this is the closest we can get to like running it live in the Colab notebook. So in this one, for example, I'm just saying, pick the map up. So this I didn't cover before, but this is actually how you tell the driving library which road network you'd like to use. So this one is saying, set the global parameter called map to the path of this thing. This local path is a function built into Scenic just to help you access something relative to the current directory. So we have in our Scenic repository an assets folder, which contains a bunch of maps and 3D models and things to help you write example scenarios. So this is one of the Carla maps. It's Town 05. And then I'm creating a car somewhere, and I'm saying its behavior is follow lane. So if we run that, it'll work for a while. This is actually pretty slow in Colab, so hopefully we'll get it all on your local machine. And then you get the GIF. So there's the car, it gets created at some point, and it's just driving straight along this thing. All right, so here's one where I'm actually writing a behavior by hand, so taking actions explicitly. So I'm saying, we'll have an infinite loop, and at every time step, let's just take some constant throttle and steering. So this looks like the kind of schematic. This part looks like the schematic I showed for the follow lane behavior before, except instead of doing something intelligent to compute the throttle and steering, I'm just hard coding. Steer left with an angle of, I think steering is between 1 and -1. So I think half is either to left or to right. I don't remember whichever. And a constant throttle, 50% throttle. If you run this, we'll get something like this. So it's just going to go in a circle because it's got constant steer. And you can see also here the physics of the Newtonian simulator are not that amazing. So it's, nothing happens when it goes off the road. Like it just goes off the road. So that gives you an idea. Here's a simple example where we're actually looking at the state of the world to decide what to do. So here, I'm saying this wait until close behavior. It says, while the distance from me, so self inside a behavior is the object which is running the behavior. From the distance of self to ego is greater than this threshold, which you can configure. Wait, the wait statement in Scenic is just like a take statement, but it takes no actions. I'm not showing that for that. And then once the distance drops below this threshold, then we'll switch to doing the follow lane. Okay. So then I am going to create 3 cars here. The ego will just have follow lane behavior. The other 2 cars are going to have this wait till close behavior. And so this shows, first of all, you can have multiple objects use the same behavior. They each get their own copy of it. So it has its own local state. And you can set parameters for them differently. So here, the default distance threshold I defined to be 3. But in this case, I'm saying the threshold should be 6 meters for that car. And then in this particular sample, let's see what happened here. Here's ego. There are the other 2 cars. They're waiting for it to get close. This one, it gets close enough, so then it starts driving. The other one, it never gets close enough, so it just stays. Maybe I'll run this one again just so you can see a different sample. This one happened to start out near an intersection, so you see this one actually randomly decided to turn left. We run it again. The dynamic simulations are pretty slow. It's a question.
For both the static and dynamic scenarios, how can I achieve reproducibility?
Reproducibility? Yeah, great question. Thank you for bringing that up. So this is something we'll talk about when we talk about the API for like how you actually call Scenic in the first place. Because then you might want to do things like run this thing and then get the same scenario and run it again, or the same simulation exactly. So here I haven't set the random seed, so you're going to get something random different each time. But you can set a random seed for Scenic so that you'll then get the exact same sequence of things happening. You can also, when you run a simulation, Scenic can save like what happened in that simulation to a file or to a little bit of data, which you could write to a file or put in a table or something, so that you could replay that same scenario again later. Yeah. So a great question. We'll talk about that. Busy.
If we set the random seed for Scenic, does it also set the random seed for simulator?
Yeah, that's a subtlety there. But in general, no, because the simulator is running kind of outside of Scenic and we don't have access to that. So that is one way that you could get non-determinism, even if from Scenic side, it's deterministic. If the simulator has non-determinism. In particular, if you think about like a nice simulator like Harla, for example, there are clouds rendered in the sky. We have no way of fixing it so you get the exact same clouds every time, right? So if you're generating images, even if we position the cars the same way and everything, you're not going to get, in general, the exact same image. If the simulator provides an API itself for setting a random seed or something, of course you can call that. But yeah, so Scenic, there is a documented API for setting the seed on Scenic side, but you may have to do something extra if the simulator itself has non-determinism. Okay. Oh yeah. So here's the second example. This one, it happened to end up on a straight part of the road, and in fact, there's 2 other cars on opposite sides, so we get somewhat different debate.
Yeah, I can see that the cars are overlapping a little bit.
Yeah, it's because this Newtonian simulator doesn't really do physics. It does like F equals ma for individual cars, basically, but it doesn't detect collisions. So this, as I said, this is really intended for like visualization, debugging purposes.
So the bounding box is only for the initial state.
I think it's point masses, right?
Yeah, but you're asking about when Scenic ensures the cars don't overlap, right? So Scenic ensures in the initial condition that they don't overlap. In the scene you generate, these cars will be disjoint, but it doesn't prevent them from intersecting later on. Yeah. Okay. Okay, no time. A few more minutes. Okay, so I think what I would like to do at this point, see if there's any more. No, so like the tutorial, the notebook for this morning, this one has a lot more variations on different behaviors and things that you can run and try playing with. What I would like to do now is show you how to run these locally, not in the notebook. So hopefully we'll be able to run these things on your own machine later on. And it'll be a lot faster than in these notebooks. But we have these if you're not able to get it running on your own machine. So let me switch over.
Well, maybe also ask if there's any questions online.
Oh, thanks, Sajid. Any questions from folks online? So I'll just show the interface Scenic has for running these things in the command line, not the special one in the notebook. And then this afternoon, we'll talk about the API for calling Scenic if you want to do stuff programmatically. And then we'll come back and just give a preview of some more advanced Scenic features that we won't have time to go into too much more detail on, but that we're happy to talk with you offline if you have questions about. Okay. So it's bigger. How's that? Is that readable in the back there? Okay. So here I've got Sublime Text because that's what I'm used to. But if you like VS Code, for example, there's also a Scenic extension for that. Just open up VS Code, go in the extensions bar, search for Scenic, it'll come up, and you can get syntax highlighting there. If you use Sublime, it's under package control. Okay, so here's like a little Scenic test Scenic program I wrote, ego equals new object. Let's see how to actually run this in Scenic. So I've made a window here. Oops. No, my window went away. Okay. So I cloned Scenic here following the instructions online. So after this session, right before lunch, I'll put up the instructions, like how to clone Scenic, get it installed. We'll go through that. So I've downloaded Scenic here, and I made a virtual environment to run things in. I'm going to call this. Oh, I thought I made one. Oh, there. Okay. We'll talk about virtual environments later. If you're not a Python person, don't know about it, don't worry. This is just where I've installed Scenic. So if we're in here, I can do like Scenic test.scenic. So Scenic provides a top-level command called Scenic for generating scenes and running scenarios. It is mainly designed to allow you to just run things to see what's going on. If you actually want to like generate data and things, you probably want to use our Python API. But we'll talk about that this afternoon. So if I run this, might be slow because it's the first time I've run this in this virtual environment. Okay, so it's compiling the scenario, and yeah, it's not normally that slow for a 1 month thing like this. See, what should come up is okay. There we go. So it's generated a scene. Oh, whoops! I'm in the wrong folder. That's why this took so long. This is a Mars rover one. Okay, this is a much more complicated Mars rover scenario with this irregular terrain. So I must be in the wrong folder. Hold on a second. Oh, okay. I am in the wrong folder. Sorry. Give me a second. You must be slow today or something. Going on there. Oops. Oh. Sorry. Now I've messed up all my virtual environments and things. Ooh, I've made too many different folders.
Are you in the right?
I was in the wrong virtual environment for this version of Python.
Are you in the right place now?
Okay, now I think it should be okay. There we go. Okay, that's more like 0.04 seconds. Why is this thing so often? Okay, so the window is unfortunately appearing on the wrong screen, so I'm going to have to move it over each time. But this is, whoops. This is like we had in the notebook, right? So it's the little visualizer. It's featured in this box at the origin in this case. You can drag it around. To adjust the camera angle, you can use mouse wheel or 2 fingers or whatever to zoom in and out. If you press Q, I think for this one, it's in the documentation, you get a new sample. So here it's generated another sample. We're going to move the window over again. It's the same kind. Okay, so I'll quit this. Let's do something more interesting. So this is just to show you the default behavior of this Scenic command. If you just give it a Scenic file, it will just go in a loop generating scenes until you kill it. So here we generated a scene in one iteration. We didn't have to do any rejection sampling. I closed it, then it generated one more. Let's do a more interesting one. Let's do that badly parked car example I showed before. So the repo has a lot of examples in this examples folder. So that one was from our Grand Theft Auto case study. It's called badly parked car 2, I think. If we run this, we're actually getting an error, I think. You get an error because this is one of the old ones, which we've kept around just so you can keep running them. This is from the day when Scenic only had 2D scenarios. So it's actually giving me an error here saying, you tried to override this heading property, which you can't do in Scenic anymore. Maybe this scenario requires the 2D flag. So we have this 2D compatibility mode flag. If you want to continue running old scenarios that were written from the days when Scenic only did 2D stuff, you shouldn't have to use this with new scenarios that you run. Except for the driving domain, we haven't actually upgraded it yet to use 3D. We're working on it, but basically getting the 3D shapes of the roads is more complicated than 2D ones. So some of those you may get a message saying you need to use the 2D flag. And some of ones from our older papers, like this GTA one, you need to use this 2D flag. That's just what that is. So if you see this error message, you just got to put this 2D flag in, so I can do that. Oh, I keep looking for the window on the wrong screen. There we go. So this is an instance of that badly parked car scenario. It's a little hard to see what's going on here because our schematics for GTA are just showing these kind of edges in this way. We don't have a nice picture of the GTA world here, but I'll just generate some more of them. Oops. Here's another. This one is a little clearer what's going on. So here's one of the cars. Looks like this is on a one-way road, and there's a badly parked car there. So if I just keep closing this window, Scenic will just generate yet another instance of that scene. So I'll close that. Yes.
Would you explain what is pruning scenario?
Oh yeah. So we'll talk about pruning later, but basically this is oops. Yeah.
You might have to close the window.
There you go. Right. I closed the whole thing. Pruning is basically a program transformation that Scenic does in order to optimize the sampling from the program. It basically eliminates parts of the space which have probability 0 of satisfying the requirements. So you don't really need to know about how that works. It's just an internal thing that Scenic does to help make things faster. But we'll talk a little bit about it tomorrow morning. And it's described in detail in the paper. Okay, so now I gotta activate this again because I closed my window. Okay, so that's for running, getting these static scenario scene diagrams, basically showing where things are positioned. So like the dynamic one we had before, the stopping and starting, we have that one in here as well. So I think that should be under like examples, driving, OAS scenarios. Oh, I don't have OAS scenario 5. That's that one. That might be on the car list. Here it is. OAS scenario 5. So this is the one that we were looking at before. This is actually a somewhat more elaborated version of it, but you see it has a similar kind of structure to what we looked at before. So if I try running this, Scenic, 2D, okay, examples, Carla, OAS scenarios, OAS scenario 5. There it is. So by default, when you run the Scenic command, it just generates scenes. So this is a scene generated from that scenario, so no dynamics. So here's the ego car, here's the lead car, which turned out to be white, so it's a little bit hard to see right now. If we close this, we'll get another sample. All right, this one's even worse. Both of them were white. I think this is using a distribution over colors that's from real data. So a lot of cars are white or silver. Here we go. Here's a more easily readable one. Okay. So these are the static scenes. Now, if we want to run this, this was designed to run in Carla by default, which I can't do on my laptop. But what we can do, I close this. This simulator is not written specifically to run in Carla. You see, it's using the driving model here. We actually have a Carla-specific model that has more stuff, but this is using the generic driving model. So, in fact, this scenario also works in the Newtonian simulator and in SVL and other simulators that implement this driving model. So, to run a dynamic simulation in Scenic from the command line, you use a different option. So, if you use Scenic -H here, you can get a summary of all the command line options. These are also described in our documentation. But one of the main ones at the top here is this -S, simulate option. This means run a dynamic simulation. So if I do Scenic-S, I put 2D again, and then I do that file, put it back there. So let's add a -S on the end. This will try to run a dynamic simulation, but then it's going to say, oh, wait, you need to say which simulator you want. So the way we can do that is we can use the model argument here. Let me move this up so it's easier for you to see. The model argument says, which world model do you want to use? And this scenario was written for the generic world model, generic driving world model here. But I can tell it to use the one for our Newtonian simulator, which basically refines the generic one here. So I can say, let's use the Newtonian simulators driving. And if I do this, it'll run in the Newtonian simulator. Now this one, I don't know if it has a termination condition, so this may just run for a while. There are other options you can use. There are other options you can use here for like how long do you want to run it for, how many simulations you want to run this up. But this is how you can run basically the things from the notebook locally on your machine. You can use this Scenic command. Once you've installed Scenic, if you want to run dynamic simulations, you can put this -S or -simulate. And to tell it to use the Newtonian driving model, the Newtonian simulator instead of Carla or whatever else you might use, you can specify that you want to use the world model for the Newtonian simulator. Don't worry about having to like write all this down. This is also in the documentation in the, I'll show it here. If we go back to the documentation, if you go to our tutorial on dynamic scenarios, you can go down to trying some examples, and we have all these commands you can use to run these things. All right, so I guess any questions on any of this? Yes.
So if I like control the vehicles, for example, I want to spin down, which is live. Can I do that? I mean, can I do it through Scenic, or I have to do it through Carla?
If you want to control like one of your
Or this attribute of the vehicle, like very the
attributes of the vehicles. Yeah.
like what like
The color.
oh
type,
yeah,
type,
right. Yes. So Scenic in the definition of the car class has a bunch of these properties which you could modify. If there's something which Scenic doesn't, so like color, for example, Scenic knows about it and it knows how to convert that into a Carla API call. If there was something more sophisticated you want to do, like suppose your simulator has some API where you can put like a decal on the side of the car, something like that.
Yeah.
Scenic doesn't know about that, so then you might have to call that API. The nice thing is, since you can call arbitrary Python code from Scenic, as long as your simulator has some Python API, you can make those calls directly. But yeah, basic things like size, color, etc. Most of the simulator interfaces understand those, and so you can specify distributions on those things in Scenic, and then it will get copied over product.
So when you're saying that new car, I can say new car and then the
With color, blah, 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 blah. Exactly.
and you can extend the driving model for that simulator and expose all these attributes.
Right. Right. So, for example, like if Carla has, like I remember, I don't know if our model actually does this, but for example, like pedestrians in Carla,
Yeah.
you can control the color of the shirt and pants separately.
Right.
So the scenic driving model doesn't have anything for that. But in the car-led driving model, you could say, okay, pedestrians have two properties, top color and bottom. You can have the interface call the car-led APIs to set those, and then you can control them.
And I'm sure that we have within the the Scenic car class, we have all the attributes, but if one has to extend something else, one can also extend that particular thing to someone.
You can, exactly. And so one of the things we'll talk about this afternoon is what is actually in this interface layer between a simulator and Scenic, and how do you write one of those?
Thanks.
Okay. All right, then let me just conclude here by mentioning some more advanced features of Scenic that I don't have time to go into in detail, but that we want you to be aware of so you can ask us about them if you're curious. So let me pull that up. Okay, so first of all, Scenic allows you to compose scenarios together. So everything we saw so far was just writing like individual scenarios and running simulations. But we can also take existing scenarios that you wrote in Scenic and put them together into more complex ones. So there is a scenario statement in Scenic like this, which basically lets you write all of the code for a scenario inside this indented scenario block and give it a name. So here we're saying, I'm creating a scenario called stop start with parked car. And what it does is it actually runs two other scenarios that I imported from somewhere, stop and start and badly parked car, in parallel. So it'll create all the objects for both of those scenarios and they'll run at the same time. You can also do a sequential composition. So this says run the start and stop scenario. And when that scenario has finished, according to whatever its termination criteria are, then start running the badly parked car. So this gets to the question that came up before about dynamically creating objects. So in this case, the badly parked car scenario will create its own objects. There will be a new badly parked car.
The objects of stop and start will get destroyed?
No, actually. So in Scenic, at least right now, objects are never destroyed. We may add something for them, but at least right now, they continue to exist. And that's basically so that any object which was created can still be referenced later on by other things. We're thinking we might add a construct to allow you to explicitly say, like, I no longer need this object, let's destroy it. But we don't have that right now. Okay. And you can do more interesting things here, like this is using an interrupt statement in this composed block to say, do the stop and start scenario, but when some condition is met, then start the badly parked car scenario. So you can actually like put some somewhat complicated logic for combining these things together. So that's one thing I wanted to mention. Scenic can also has various features to help you orchestrate simulations. So if you want to record data, we'll talk more about this later. But Scenic has a record statement, which lets you save the value of any Scenic expression, either at every time step. So here we're saying at each time step, save whether the ego can see the pedestrian or not as this record called head visible. And when the simulation is done, Scenic will return to you a little object which packages up all this data. You'll see that this afternoon. Or we can just save values like at the beginning or the end of the simulation. So here we're saying save the distance goal at the end of the simulation as end distance. So you can tell Scenic basically what information about the simulation you would like to save, and it will collect that for you. I also mentioned this before, you can save and replay scenes and simulations. We'll look at this API in more detail later, but basically here, I'm using the Scenic Python API to compile a Scenic scenario that's in a file, sample a scene from it, and then convert that scene to some bytes data, which I could then send to somebody else, and then they can exactly reconstruct that same scene. So not have to worry about set a random seed or anything like that. You get the exact same values. And we also have integration with Verify, which Sanjit mentioned before, so that you can do things like not just sample values for things randomly, but search intelligently for values and parameters that lead to collisions or things like that, using optimization algorithms, things like this. And this will also come back to tomorrow.
Tomorrow.
Yeah. Okay. And then the last thing before we end our morning session, we switch to logistics stuff before lunch. I just want to make you aware of some of the places you can look to learn more about these things. like tonight or going forward after this workshop. We've got the main website that I mentioned before. The documentation is linked to everything's linked to from there. In particular, the documentation, sceniclanguage.org has installation instructions for all major operating systems. We've got expanded versions of the tutorials we did today. I pointed out before the syntax guide, which is a relatively short page that summarizes all the constructs in Scenic. And we also have the language reference, which has all the gory details. There's Python API, which we'll talk about this afternoon, and also interfacing Scenic, we'll also talk about this afternoon. And then finally, we also have a community forum, which we just recently started. So there isn't much there right now, but if you have any questions about Scenic, we encourage you to ask there. Our hope is that it can become a resource for people to look up answers to questions that people have previously asked. So those of us on the Scenic team who are monitoring that, we're happy to have discussions there about how do you use a particular Scenic feature, advice on interfacing to a simulator you're interested in, prospects for adding some new feature, anything like that. Okay, so that is it for this part of the tutorial. So the next thing we're going to do before lunch, we've got lunch coming up in like 25 minutes or so. We're going to have some time to help you get Scenic installed on your computers. So I put up here the one slide installing Scenic. However, if you go to the Getting Started with Scenic page, there's links there and it can be customized for particular operating systems. So I would actually try that. But this is like the Linux or Mac one slide version if it's helpful.